Okay, AGS1. Like I told you guys in class, we're splitting up Chapter 2 into two different tests. The first test is just going to be over 2.1 through 2.4. In 2.1 through 2.4, we talked about domain. Remember, that's all the inputs that can go into a problem. Sometimes domains get restricted based on the context of a word problem. Like if you're dealing with time, you usually can't have negatives. It has to be positive numbers, stuff like that. There's two different kinds of domains. There's discrete domains and continuous domains. If you are looking at a discrete domain, those are unconnected dots. There's breaks between the numbers, and it's usually natural numbers. It's usually the result of counting whole numbers. There's no decimals or anything like that. So a classic example would be like the number of students in a class. Because you can't have, 22.5 students. It's always whole numbers. Continuous is the opposite of that. That's where you get to connect the dots. There's no breaks. The dots are connected, and change is always happening. An example of that might be race times in 100-meter dash. We've been focusing a lot on arithmetic sequences and geometric sequences, but in this unit, arithmetic sequences have been referred to as linear functions. Geometric sequences have been called exponential functions. Remember, with arithmetic sequences, you should be able to spot a common difference. That's the number that's being added or subtracted. If you were to plot the points on a graph, they should make a straight line with a common change. And you guys should know by now how to make an explicit equation out of those. Same thing for geometric sequences. I guess I should have added explicit here. Know how to spot a common ratio from a table or something like that. And an example, a classic geometric sequence example, something that involves percentages. If you were to plot an exponential / geometric on a graph, you get this nice Superman graph where he's taken off into the sky. The main thing there is that it's curved. Now remember, not every curved graph is geometric, or exponential, but every exponential graph is curved. So there's some curves that are non-exponential. We've been focusing a lot on the connection between tables, graphs, and equations. I think given a table, you guys should be able to make a graph. That's just plotting the points. And vice versa. Sometimes we'll give you the graph, and then you can put it into a table. You should be able to take a table and turn it into an equation if it's linear or exponential. Remember, sometimes there's gaps in the table, so you have to watch out to make sure your x values or n values are going up by, a certain amount each time. Certainly, given an equation, you could definitely come up with a table where you can pick certain x values, plug them in, and then put them in the table. Now, let's see, graph to equation. I don't think we really did that too often. I think usually we had to go this route first, where you turn it into a table and then into a graph. Or if I gave you a graph trying to turn it into an equation, you would have to go this route as well, turn it into a table first and then over to the equation. I think later on down the road, we'll get better at this, of going between